related rates problems that I'm trying to decide between. And so I think what I'll do is pick one. Then sometime this coming week, this will be the hard part for me, is I will just do half a class. Then if you don't want to take the extra credit deal, then you're free to leave. The people who want to will remain and have the time to do one related rates problem, which again can only add points to your test. And I'm willing to say 10, I've decided. Does this sound in the ballpark of acceptable to everyone?
Yes.
Yeah. So the question is, what day should it be? Monday and Tuesday I think are a little too soon.
Thursday or Friday.
So Thursday or Friday. Of course, you see what the attendance, I mean, on Friday it seems like our attendance is getting kind of thin, and
it's motivation to be here.
Yeah.
Yeah. Just send the announcement.
because, but see, the calculus should be enough motivation. Learning.
Yeah.
Some people don't feel that. I mean, you know.
I guess I need to accept that.
Not saying that they should.
I feel like this is a class we should fix, so I don't know.
Well, it's a hard time of day for college students. I do get that. But okay, so Thursday or Friday next week, one related rates problem, and it's going to be something that I think is reasonable for everyone to be able to do. Not exactly the same as something we've done in class, but similar reasoning processes, similar objects and stuff like that. So here's what you need to do is, if you're a person who wants to do this opportunity, then between now and then, see, the pressure of this test is sort of off, so time to focus on related rates. Go over the homework problems you had in that, go over the examples that were in the book in class. Okay, and that will be my best advice, because I will pattern it after something there. The ones we did in class that were examples in the book, and then the assignment in related rates, whatever that was. What was it? 2-7. Okay, thank you. All right, so that's next week. I'm calling it Test 2 Redemption Opportunity. Stacy, if you don't mind, there's something I wanted to ask you in the class. It's not anything bad.
I was like, what did I do?
Just I don't want to forget. I was going to ask you before class, but I okay. All right. So no, you did not tell me.
Those bug eyes I made at you yesterday when I got lost, right?
That did scare me a little.
It scared me too.
Yeah.
Okay, so anything you all want to ask before we get started finishing up 3-3, which we're going to do today? Well, we are going to have some new formula, but nothing that we have to go back to the limit definition of a derivative for. We'll just use the one we developed yesterday and to get some nice other ones. But they're nice and easy, and they'll be helpful to us. So, and we're going to explore a little bit further this idea of how those rules of logs can help us and make our work easier. Remember that problem I showed you yesterday? How it was much quicker, less possibility of error, if you remembered to use the laws of logs first before you ever took y prime. So more on that topic. So anything to ask? Okay. So you know how the absolute value of x, that's a really important function we talk about from now and then. So let's start with that. Suppose f of x was the natural log of the absolute value of x. Now, if it was just the natural log of x, what would its derivative be? We got that yesterday, and it gave us a nice, easy one.
1 over x.
1 over x, that's right. So we'd like that to still be the case when you're differentiating the absolute value of x. So let's check it out. Well, okay, you know how this thing goes. This is one of two things. This is either going to be the natural log of just plain x if x is greater than 0, and it's going to be the natural log of the opposite of x if x is less than 0. All right, two questions for you. First question, why don't I have anything over in here about what if x was equal to 0?
X can't be 0. Denominator can't be 0.
It's
No,
but you're right, it can't be 0. That just wasn't the reason. So
you can't find the absolute value of 0?
you can't find the natural log of 0.
Okay.
Remember, the domain of the natural log is positive reals. Remember how that thing does this shape? It has a vertical asymptote along the y-axis, never hits it. So x can never be 0. So I don't need a rule for x equals 0. Okay, now, why does this look so weird? Because take the absolute value of x, I'm supposed to get something positive here. What am I doing with this negative sign in front of it? Anybody want to explain that? Because you all know. On some level, you know it.
Wouldn't it still be positive?
It'd still be positive, Jennifer. You're on fire today. Yes. Because see, this is the case when x is already a negative number, like negative 11. So what this does is put another negative in front of it to make it something positive. Okay. So that's the natural log of absolute value of x. So then that would imply that when we go to take f prime of x, it would be one of two things. All right? Let's take this first case when x is greater than 0. We're just going to need to take the derivative of natural log of x. Well, that's 1 over x. No problem. The second case, if x is less than 0, then what we're going to have to do is put 1 over negative x, right? Because natural log of this, or 1 over the opposite of x. However, in this case, you're going to have to then multiply by the derivative of the inside part, which is negative 1, which is just 1 over x for x less than 0. So in either case, the derivative of f of x is just going to be 1 over x, no matter what kind of x value you have. So that absolute value sign doesn't mess us up at all. The derivative of natural log absolute value of x is still just 1 over x, whatever kind of x we have. All right, that's good to know. Let's do our little three balls here. Therefore, f of x equals natural log absolute value x implies f prime of x is still just 1 over x. Okay, now, because of the thing that we noticed yesterday, the fact that we noticed yesterday that those laws of logarithms are very useful before differentiation, because you have something that's a division, and all you need to do is use the laws of logs to make it a difference, you know, that kind of thing. So we want to use that fact, and we want to use it on snarly problems that might look something like this. Now this is called logarithmic differentiation. And I want to make the case today that it is your friend and it is going to make your life much easier. So I'm going to first do a problem using what is called logarithmic differentiation, and then I'm going to show you where I worked the problem without it. And you can decide which you think looks simpler, you know, and less prone to error. Okay, say y is something like this. X to the 3/4 power times the square root of x squared plus 1 divided by 3x plus 5 to the 5th. Now, could we differentiate it just using rules that we already know? Absolutely. And it's not really that terrible. However, look within that. Overall, it's a quotient, isn't it? Mm-hmm. So you're starting out using quotient rules. So you're going to say denominator times derivative of numerator, which is a product. So within that, you're using the product rule. Furthermore, you've got chains in here because of this, right? Yes. And in the denominator, another chain rule when you get to differentiating it, and over denominator squared, now we're to the 10th, okay? There's some work involved here. So I'm going to suggest a thing called logarithmic differentiation. Now notice, there aren't any logarithms in this problem, are there? We dream it up. Now you don't have to worry about when to use it, because I'm going to say on your next quiz and on your next test, I will say use logarithmic differentiation. So you know that on that problem, that's what I want you to do. Now there are some problems a little bit different than this where you have to use logarithmic differentiation. But on this one, there's an option. You could do the quotient rule and chain rule and product rule and all that stuff. Mm-hmm. Okay, so suppose this was, I just said use it. Now here's the key thing. In the first step, we are going to take natural log of both sides. And that's something you can do, right? There's a rule of logarithms that says if you have a left and right side that are equal, you can take logs of both sides. It'll still be equal. So there's your choice right there. Natural log y equals natural log of all that stuff. X to the 3/4. Well, let's go in and write that square root as that to the 1/2 power. X squared plus 1 to the 1/2 over 3x plus 5 to the 5th. So natural log of the left equals natural log of the right. So there's your first step. Now, on the left, we leave that alone for right now. Notice, not going to take the derivative yet. There's all kinds of stuff I can now do on this right side to simplify it. Natural log of top minus natural log of bottom. And then on the top, you know how these powers are going to come out to the front, and I'm going to take natural log of this plus this, and all kinds of things are going to fall out there. So this is going to be natural log of the top, x to the 3/4 times x squared plus 1 to the 1/2 minus natural log of 3x plus 5 to the 5th. But that's the natural log of y is, all right, see this is time, so now I can split this up, say it's natural log of the first plus natural log of the second. And will y'all let me bring the powers on out to the front in the same step? So that's going to be 3/4 natural log x plus 1/2 natural log x squared plus 1 minus 5 natural log 3x plus 5. So now instead of a quotient and products and powers and stuff, I've now just got something like this. Now check out how easy this will be to differentiate. Okay, 3/4 times 1 over x plus, yeah, Jennifer.
Where did you get the plus sign between 3/4 natural log of x? Because it looks like it, yeah.
Okay, it started out, this was times. Mm-hmm. So I'm using that rule of logs that says natural log of m times n is natural log of m plus natural log of n. It's that, yeah. Okay, so now I'm ready to, yes, 18.
Would it be correct if you talked about the natural log?
No. In this case, you see, it's natural log of different things. If it was the same thing you're taking the natural log of, yeah. But in this case, we like this natural log sitting here. It has the easiest derivative ever, 1 over that thing, right? And that's what we're trying to do, is take the derivative here. Now there's a little bit of a complication on the left side because it's no longer just y. So when I take the derivative of the left, you're doing it like implicitly. 1 over y dy dx. Okay, so there's that. So let's do that. We're now taking the derivative. So 1 over y dy dx, or y prime, whatever you want to say. But then on the right side, I'm going to have 3/4 times 1 over x plus 1/2 times derivative of natural log of this is 1 over x squared plus 1. However, what do I have to do now? Chain. Multiply by 2x, right? Times 2x minus 5 times derivative of natural log of this would be 1 over 3x plus 5, and it must be times 3. Chain rule again. So, now, do you see this? I could get dy dx alone, which is the point of taking the derivative. You wanted to say y prime equals, so dy dx, but I'm going to have to take both sides of this equation times y. Then that'll get my dy dx alone. So I'm going to have 3 over 4x plus, now see these 2's go away? 2 over 2, multiplied by 1. So I do have x over x squared plus 1 minus 3 times 5, 15 over 3x plus 5. All right, there's the bracketed stuff. But I do then have to multiply by y, and you want to go back to its original form, which is all this stuff. So x to the 3/4 square root of x squared plus 1 over 3x plus 5 to the 5th. And that's our answer. I know it's not real pretty, but it's, that's it. Now, really, I have written down more things than you have to. And I know some of y'all are thinking, why did she write all that stuff down? So, right here, now you have to do this natural log of both sides. But I could have omitted this line right here and gone straight to bringing those exponents out front and saying plus here and minus here. You can go straight to that if you're okay with that. But, and arithmetically, it's not snarly, is it? I mean, really, because of this derivative of something, a log of something is just 1 over that something. That's what makes things so simple, as well as the rules of logarithms. Now, I see if maybe there are a couple questions out there. Anybody want to ask something? Maria.
Why is it that we multiply it by what we have first?
Okay. When I did this step right here that allowed me to use those rules of logarithms, on the left, I don't have y anymore. I just have natural log of y.
Right.
So when I differentiate that side, I'm doing it implicitly. So it's derivative of natural log of y, 1 over y, but then dy dx, because I'm differentiating with respect to x. Okay, so to find the derivative, well, that's not 1 over y dy dx. It's just dy dx I need alone. So I need to cancel this y out. So that means I have to multiply it so that this happens. Well, if I do that on the left, I have to do it on the right. And I don't want two variables floating around in here. I know what y is in terms of x, so I just, yeah. Now, so you all see, you could have omitted this step right here, so that it's really just 1, 2, 3, 4 steps. Yes, Stacy.
So on the last part that you have boxed, if we were to do everything in the parentheses, And just do times y, would that be incorrect, or do you want that y substituted back in so you have the entire original problem?
Well, it'd be considered bad form to leave y as y. However, it is right here. I mean, but grading the paper, I would look at the y there, and I would interpret it as laziness, to tell you that. You just didn't want to write that y.
Well, I'm just curious, because
But it wouldn't be wrong. No, I wouldn't count it wrong. Yeah. Amanda?
What happens so that on that line where you multiplied everything by y?
Yeah.
What happened to that put the x squared plus 1 and also the 3x plus 5? What happened that put that in a denominator under 1?
Oh, when I took the natural log of x squared plus 1, it's 1 over whatever that is. Because that derivative of natural log of x is 1 over x. Remember, we just had it yesterday.
That's right. That's
Yeah.
right. Okay.
Yeah, that's the actual taking the derivative that puts those in the denominator.
And we don't need to put any dy dx's over here unless a y appears, since it's the derivative of, or since it's the natural log of y.
I had to put dy. There weren't any y's over here
Right.
at this point. And I was differentiating in terms of x, so I could just differentiate as usual. But on this side, if it had just been y equals, then you differentiate and you say dy dx, right? But it's not that, it's natural log of that. So natural log of something, derivative is 1 over that something. So that's where we get this, and then we have to say dy dx, because we were differentiating with respect to x. That's an implicit thing. Vicky?
That's why you multiply by y, because you did 1 over y. So then you multiply by y to get.
I multiply by y because I want this alone. Exactly. Yeah. Yeah. Okay, now here's your motivation here. Let's say that you don't like the logarithms and you don't want to do that, because I did tell you you can do that problem without it. This is what you have to do. That's the quotient rule with the product rule and the chain rule and the blah, blah, blah.
Yeah, you missed that one side, the whole thing.
That's right. That's right. That's what you'd have to do. So reconsider how friendly these logarithm rules are.
I love logarithms.
And see, that's, when you look at the problem at first, it doesn't really look that horrible, but once you get to doing all this stuff, there's a lot to do. Okay. So, I'm only putting this, I'm not going to subject you to going through it, I just want shock value. Okay. Do you want that in your notes or not?
no.
No.
I do. So far, we have that if y is the log base a of x, this was the first one we got yesterday, that implies y prime is 1 over x natural log a. And if y is the natural log of x, that implies y prime is just 1 over x. Okay, so we have those two. Now, this is just for entertainment. This is just for your entertainment. Suppose we had, you don't have to write this down. Say we had y equal x to the n. Well, that's just power rule, isn't it? And we already know the derivative of that. We did it by the binomial theorem. However, suppose we use logarithmic differentiation on it just because we wanted to amuse ourselves. We would get natural log of y is natural log x to the n. So the n comes out front. So now we take the derivative. So 1 over y dy dx on the left is n times 1 over x. So dy dx is n times 1 over x
Times X.
times y, right? Because this is the step where I'm multiplying both sides by y to get dy dx alone. However, that's n times 1 over x, and y was x to the n. And that's n times x to the n minus 1. So there are problems that we've done other ways that you can use logarithmic differentiation on to just kind of solidify our knowledge. Isn't that cool? New way to do that. But you already know it, so let's go on. Say we have f of x equals a to the x. Now this one's going to be new. Okay. So do you see how this is not a power thing, is it? A is a constant. Remember, Stewart uses a for a constant. And the power is x. And so we've got the variable that we're differentiating with respect to up in that power. So this is going to be different, and it's really laws of logs that would allow this to come out to the front. So that kind of might motivate you to think, well, maybe I should take natural log of both sides. So that we have x natural log of a. Now natural log of a is a constant, right? A is a number. So we differentiate 1 over y dy dx is, okay, so x here is multiplied by this constant. When I take the derivative of the right-hand side, I just get natural log of a. Now I need you, will you nod your head if you see this? It's a number times a variable to the first power, so the derivative is just that multiplier. Okay, so multiply by y on both sides. Dy dx now will be alone. Y, natural log of a. But y was a to the x, natural log a. So this is new for us. This is not hard. Maria.
So why do we use the chain rule when we have x natural log of a if we took the derivative of x and a natural log of a was in parentheses?
Okay, you mean the product rule? Are you thinking it looks like a product?
Yeah.
Okay. Okay, here's why. Another way I could write, let's take this and haul it over to the side here. Okay, couldn't I write that as natural log ax?
Oh, yeah.
That's the same thing, isn't it? Okay, now remember, I know a looks like a variable, however it is not. A and B and C and K in this book are typically meant to be some constant number like 7 or whatever. They're just not going to say what it is. So this is like as if I had 4x here and take the derivative 4. It's like that.
Okay.
Yeah, it looks like a product, I agree with you, but you have to remember a is just a number. So when I take the natural log of that number, it's some number too. Okay, so the derivative of a to the x is a to the x natural log of the base, whatever that base was. All right. So we could use this if I had something like y equals 10 to the x squared power. Now, I'm not going to use logarithmic differentiation this time, though I could. I'm just going to use this rule. Because 10 is a here. And then I have an exponent that's some kind of function of x. So this rule is going to tell me the derivative is 10 to the x squared natural log 10. However, we still have to do chain rule. And the power has a derivative, which is 2x. So y prime is going to be 10 to the x squared, like this, natural log 10, but then I have to multiply by 2x, as y'all told me. Now, I really don't know how to make that look any better, but I think that, I think Stuart pulls the 2x out front. 2x 10 to the x squared natural log 10 or something like that. Or maybe he does 2x natural log 10 times 10 to the x squared, I don't know. But do you see how I'm not doing anything in these steps? Just, oh. Just rearranging. So this, or this, or this, are all the same. There's nothing, just, I mean, see, the possibilities of messing up abound. Because your inclination is to tidy up. You want to take this 2 and multiply it in here by, no, because this 10, we're taking the natural log of 10. This is some number. It's e to what power is 10, you know, it's that kind of a thing. And it'd be like 2 point something, I guess. And so that's a number, and then we have 2 times the variable and 10 to the x. So nothing combines. Nothing combines. And it's really good, it's like a good life lesson too, because sometimes the hard thing and the important thing is to know what not to do, or what not to say, or, you know, when you just really want to do something and you know you just can't, it's bad. Yeah, Amanda.
Sorry, I think you already said why we did it, but I'd like to get it in my notes. On the second line, what gave us permission to take 10 to the x squared and multiply it times the natural log of 10? What rule was that?
Okay, it's looking at you right up in here. I'm applying this newly derived formula for the derivative of a to the x. Here a is 10, and it's not just plain x, but it's some function of x. So this is an example of this rule right here. The derivative of a to the x is a to the x natural log of the base. So derivative of this is 10 to the x squared. The natural log of the base is 10 there. And of course, you know, natural log, that base is e, right? So natural log of 10, that's not 1. Wouldn't it be 2 point something? What is it? Natural log 10, 2.3. Something like that. What power do I raise e to get 10? You know? Takes a little while to set in. Yes. All right, so how about this? This is a cool one. Suppose y is e to the x. There are many ways to show the derivative of e to the x, but we're going to use this to do that. Here, e is our number a right here. And so you can go straight away using this rule and say derivative of e to the x is e to the x natural log e. But what's the natural log of e? So this is stunning right here. the derivative of, here we have, now I've been saying all along many times, sometimes y'all do y equals something and then you start taking the derivative and just keep on going with equals, as if a function and its derivative were the same thing. Well, here's an example when they actually are. So one other way to think about this is the okay, you know what e to the x is? It's that growth curve, right, going through 0, 1. Okay, at any point on that growth curve, the slope of the tangent line at that point is e to whatever the x coordinate is. Because the slope of the tangent line is the derivative there, right? So the slope of the, say x is 7. What's the slope of the tangent line to that curve right there? E to the 7. Getting real steep there, yeah. Yeah. All right. That was the funnest one right there. It went too fast. Okay, just a little more then. Suppose that y is e to the tangent of x power. So we're using the same rule here that you're looking at right up there. It's just the power is another function of x. So y is going to be y prime is going to be copy the same function. Y prime is e to the tangent x power, but then I have to multiply by the derivative of that power. Not up in the power, but times the function. So what is that?
Secant squared.
Squared. That's it. That's all you have to do. Okay. Suppose I had y is e to the negative 4x, and it's times the sine of 5x. Now that we've got all these different rules, they're all going to be mixed up in the same part. So here we go. Overall, what is this thing?
Product.
It is a product. So we're thinking of this as the first function of x, the second function of x. Both of them have an x in them, so we're differentiating. So y prime is going to be the first, e to the negative 4x, times the derivative of the second. Anybody want to help me out?
Cosine.
Cosine 5x, am I done? Times 5. That was so enthusiastic. Was that you, Andrew? 5. Who was that? Okay. Well, yes, times 5. I'm just sorry. Okay. So first times derivative of second plus second as it is sine 5x times derivative of first. What's the derivative of e to the negative 4x? E to the negative 4x, right? Am I done? Times negative 4. Yeah. Now, there really is not anything left to do except for we could make it just look a little bit better, because they both have this little complicated thing, both meaning now new first term, new second term. I could take that out front, e to the negative 4x times, and this 5 could come out front, 5 cosine 5x. Now, see, I have a minus 4 times the second term, so minus 4 sine 5x. I like this better. I would not count the previous line wrong, however. And Stuart's going to do this, bringing these constant multipliers out front and putting this little complicated thing that's times both terms out front using the distributive. Last example. And it looks strange. Y is x to the square root of x power. Now see, we can't use the power rule because the exponent's not a number that we could subtract 1 from and all that business. And we can't use a to the whatever rule, a to the x rule, because this is not A, this is not a constant. So therein lies the problem. We don't have a constant either here or here. And so the solution lies, of course, as you might guess, in logarithmic differentiation, because then we can pull this out front. Now it's product. We know about products. So natural log y, though if I gave you this problem, I still would say use logarithmic differentiation. Natural log y, okay, I'm going to pull this out front. Square root of x, natural log x. So, the only other thing really to do is I could say that this is x to the 1/2 natural log x and put my parentheses in so I'll remember to use the product rule, but that's kind of optional because the square root of x is x to the 1/2. Okay, so now here we go. Derivative of the left side, got to do implicitly. So 1 over y dy dx is first function x to the 1/2 times derivative of second, which is 1 over x, plus the second natural log x times the derivative of the first. Somebody help me with that, Andrew? Will you help me?
1/2 x to the negative 1/2.
1/2 x to the negative 1/2. Now here there is a little bit we can do. Dy dx then is going to be y times all this stuff, right? All right, this is x to the 1/2 over 1. Well, that's the same as x to the 1/2 minus 1, which is x to the negative 1/2, isn't it? Then, this other thing, plus 1/2 natural log x, x to the negative 1/2. I don't know. And here's the question, what do we do? Well, I do want you to say what y was. It was x to the square root of x power. I kind of think Stuart would pull this x to the negative 1/2 out front. And I actually forgotten what he does. I mean, it's okay like it is. I'm just trying to make it look a little bit better. You could say this is 1 over x to the 1/2 plus natural log x over 2 x to the 1/2. But you see how we're not really going anywhere. We're rearranging people on the bus, but the bus is at a dead stop. So, I mean, I'm okay with that. You could take the x to the 1/2 out front. Just don't think that it would combine with this, because it wouldn't. Amanda.
What happened on the second to last line to make the y times, and then you have x to the negative 1/2?
Mhm.
What made that negative?
X to the 1/2's in the numerator, and it's divided by x to the 1. So x to the 1/2 minus 1 is negative.
Okay.
Yeah. Okay. So play with these problems in 3-3. I think I mostly just picked ones out of 3-3 for your quiz next Wednesday. You want to do really well on that. I'm not totally sure about that though, but I'll let you know Monday. So anyways, make sure you've got these down and review your related rates problems.